Question that appeared in one of our recent tests. I want to use this to show you how to solve a lab-based question. So I'm not going to take the time to show you how to get parts A and B. That doesn't really have to do with the lab aspect of this. But what does matter is that a question like A and B, those questions are very typical as an introduction to a lab-based question in the sense that you have to derive an equation. And so just to tell you what the answer to part B was, if you did this derivation correctly, you would have gotten the square root of 2dg sine theta. So the result of doing parts A and B would have given you that right there. Here's why that's significant. Let's take a look now at what they're asking us to plot. It says the table to the right shows the results of multiple trials for this experiment. Use the data to create a linear plot in which speed at the bottom of the board will be plotted on the y-axis. And that's really important, by the way. Please always read these questions carefully. It will often tell you what you're supposed to plot where. So when we make a graph, we want to have speed and not speed squared or the square root. We want to have speed on the y-axis. And obviously, we want to have something having to do with distance on the x-axis. So how do you figure out how to manipulate the data in order to create a straight line? Well, there's basically two ways of doing that. One is to just plot the data as given and see what shape that makes. In fact, let me try that first. This isn't always the best method because it takes time, but I think it's good to see it as practice. So I'm just going to use some graph paper, and I'm going to plot speed on the y-axis and distance on the x-axis. I thought I'd show you how I plot this just to give you a little insight into my thought process, because it can be a little intimidating there to see that blank space and know how to set up a graph. So one thing we're going to take a look at is the range of the data. I'm noticing that the speed data goes from 0 to 3, and the distance data go approximately 3. The distance data goes from 0 to a little over 1. So I'm thinking if I have an axis here, I want to have squares that are divisible by 3. So literally, I'm just going to do 3 inches here. So that's a y-axis that's 3 inches. So it would make sense then that this represents 1, this represents 2, and this represents 3. My x-axis, remember my highest number is 1.25. I think maybe I will go, just to make it big, because that's the other thing. You don't want to have a small graph. But just to make it big, I'm going to go to 4 inches, which would mean if this is 2, this is going to be 1. And now I just have some space to plot this data. So let's take a look at that data. Try to get it in the screen here with everything else. So there is 0, 0 on this data point. There's 0.25, which would be here, and 1.31, which would be right around there. Then I have 0.5, which would be here, and 1.98, almost 2, so right around there. I can see a curve emerging already. 0.75, which is here, 2.41, which is right about there, 1 and 2.62, so right about there, and 1.25, which is here, and 2.98, which is almost 3. So it looks to me like I have a trend that looks like that. Now, why is that helpful? Well, something that you should probably memorize is what these various shapes indicate about the proportion between the two variables. When you get a shape like that, that is basically indicating that y is proportional to the square root of x, although it could be the cube root of x or the fourth root, but typically it would be the square root. And you should review those shapes. The other two common shapes, it would be a shape that looks like that, where y is proportional to x squared, or maybe x cubed, or maybe x to the fourth. You can also get a shape that looks like this, which is y is proportional to 1 over x, or possibly 1 over x squared, or 1 over x to the third. So you should memorize these three shapes and what type of proportion they indicate. So this tells me that basically velocity is proportional to the square root of d. And that tells me what I need to do to create a straight graph. So a straight line always occurs when, grab a different page here. A straight line always occurs when y is directly proportional to x. If what you plot on the y-axis is directly proportional to what you plot on the x-axis, you'll get a straight line every time. Now, we just plotted v versus d, and we did not get a straight line. That's because v is not directly proportional to d. I can't plot v versus d and get a straight line because they're not directly proportional. But what this shape indicates is that v is directly proportional to the square root of d. Think about what I just said. V is directly proportional to the square root of d. So what's inside this square is directly proportional to what's inside this square. Therefore, if I plot v versus the square root of d, since those two things are directly proportional, I should get a straight line. So that's always the goal. You want to plot two things that are directly proportional to one another. Let me just back up for a moment and explain to you how you could have bypassed making this graph entirely. Like, how could you have known the proportion to plot without even making this graph? Well, if you get an equation that you've derived ahead of time, look at this equation right here. What do we see in this equation? We see v on the left-hand side, and sure, there's a lot of things here, but ultimately we see d. Distance is the other variable that we were interested in, and it appears right there. It appears under the square root sign. So this equation was telling us that v is proportional to the square root of d. So if you have to derive an equation before dealing with some data, take a really good look at that equation that you derived. Nearly 100% chance that that equation itself will tell you how the two variables in your table are related to one another. And if that fails, if you can't do that, then go ahead and plot the original data and see what kind of shape you get. So anyway, I now know that I need to plot speed versus the square root of distance. That means, of course, I have to calculate that. And on the AP exam, on my tests, I will be looking that you put that in a data table. So let's label that correctly. I want to calculate the square root of distance. The units for that would be the square root of meters. If you manipulate the variable, you got to manipulate its units in exactly the same way. So I'm just going to go through this table, use my calculator, and take the square root of these different values. So the square root of 0 is, of course, 0. The square root of 0.25, I believe, is 0.5, yes. The square root of 0.5 is 0.707. The square root of 0.75 is 0.866. The square root of 1 is 1, and the square root of 1.25 is 1.12. So now I want to graph this on my x-axis, and once again, speed on my y-axis. Never manipulate your y-axis data unless they ask you to, which would be rare. It's so much easier, I'll show you why later, to manipulate your x-axis data. So here again, I'm going to make a graph. I'm going to plot speed on the y-axis. So once again, I think I'll do 3 inches for the y-axis. That seemed to work well last time. So there's 3 inches. So this is going to be 1. This is going to be 2. This is going to be 3. And my highest value down here is 1.12. So I'll probably do about the same thing I did last time, which is make 2 inches equal to 1, and over here would be equal to 2. So let me draw this line. Now here, since you're being judged on this, you got to label your axes. That is something that'll either give you or lose your points. So this is speed measured in meters per second. I've got the variable, I've got the units. This is square root of distance. I could put just d there, square root of d. But units are square root of meters. Make sure you have the units also. And so now I'm going to start graphing. And I got a couple different numbers I have to look at. 0, 0 was on this graph. My next x-axis point, sorry for going back and forth here, but my next x-axis point is 0.5, and that goes along with a y-axis point, a speed of 0.31. So 0.5, 1.31. 0.5, 1.31. I want to try to be accurate here because I'm going to be getting a slope of this. Looks like there. My next x-axis is 0.7, and that goes along with 1.98. So 0.7 would be right about here. 1.98 would be right about there. Now we have 0.866 and 2.41. So 0.866, where would that be? This is 0.75 here. So 0.866 and what was that other number? 2.41. 0.866 and 2.41 is right around there. And then I have 1 and 2.62. 1 and 2.62, I'm going to say is right around here. And then finally I have 1.12, 2.98. So 1.12 is probably here. 2.98 is probably there. So maybe not a perfectly straight line, but data often doesn't create a straight line. Now what you want to do, because you're going to be finding a slope, is you want to draw the best straight line that you can through this data. And that is an eyeball situation. Different people are going to have different agreements on that. So that's my graph. And let's just review what makes this a good graph. I've labeled the axes: speed, meters per second; square root of distance, square root of meters. I've used a ruler to draw a straight line. I've plotted the data. So we're ready to go with the next part of this question, which is find the slope of your graph. We got to show our work, and let's do that. Now, when you find the slope of the graph, what you need to do is use 2 points that are part of the line but not part of the data itself. That's really important because you'll notice that some of these data points are a little bit off the line. Even if you have a data point that's right on the line, find 2 unique points. And I find that grabbing them from as far apart as possible is best. So I'm going to grab one data point from, I want to choose something easy. So this is a half, this is 0.25. Maybe I'll take one from 0.25. And that coordinate there would be x equals 0.25. And what does y equal there? This is 0.5. That's 0.75. As an approximation, I'll say around 0.7. Not perfect, but you're going to have a little bit of an approximation. And then over here, maybe I'll use 1.25. And when I go up, well, you know what? I think I can still approximate what that is. So that point right there, x equals 1.25. And what does y equal? It's just a little bit above here, a little bit above 3.25. Let's say maybe 3.28. Again, this is an approximation. So now to calculate the slope, of course, slope is equal to y2 minus y1 over x2 minus x1. So y2 is 3.28 minus y1 is 0.7 over x2 is 1.25 minus x1 is 0.25. So using my calculator, 3.28 minus 0.7 is 2.58, and then that's actually going to be divided by 1. So the slope here is 2.58. The units would be the units of the y-axis, meters per second, divided by the units of the x-axis, which is square root of meters. You could simplify that, but just for the sake of time, I'll leave that the way it is. So that is the answer to part D. Now let's take a look at what part E says. Write the equation of the line that relates V and D. And this is the whole reason you make a line, is because we know the equation for a line is y equals mx plus b. So this is a very simple matter of replacing the y with the variable that's on your y-axis, which is v, and replacing the slope with the slope that you calculated, 2.58, and replacing the x with the variable that's on your x-axis, which is not d. Be careful about that. It's square root of d. That's a very, very important thing. You did not put distance on the x-axis. You put square root of distance on the x-axis. Now the y-intercept, 9 times out of 10, that's going to be 0. Don't input numbers to find the y-intercept. Just look at your graph and estimate the y-intercept. And certainly with mine, I would estimate that it's 0. So I'm going to call that my equation for that line. Let's take a look at the last question, which says use your equation and the expression you derived in part B to determine the angle of the incline. So this is a very typical final question. My expression is V equals 2.58 times the square root of D. And back in the first part of this, when we derived that equation, I didn't show you that part, But if we had done the derivation, the correct answer is v equals the square root of 2dg sine theta. And so this is very, very typical for the last part of a lab-based question, where you have two expressions, one that comes from your graph and a theoretical expression, and you simply set them equal to each other. They both equal v. So 2.58 square root of d is equal to the square root of 2dg sine theta. And then you can go ahead and simplify that and get your answer. Just a quick comment. This is why we plotted v on the y-axis and we didn't do the v squared or any manipulation of v, because we already had an equation that said v equals something. So we wanted our equation to say v equals something, so we could easily set them equal to one another. Anyway, the rest of this is math. I suppose I would square both sides. So if I do that, 2.58 squared is equal to 6.6564. And then we're just going to have d instead of square root of d. Squaring this side gives you 2dg sine theta. The d then cancels out, and this is very typical that one variable will cancel out. If you can't cancel out a variable, it's a sign that you probably did something wrong. I'm trying to solve here for, what variable am I solving for? To determine the angle. Okay, so I'm solving for theta. So if I do that, sine theta is going to be equal to 6.6564 divided by 9.8. And so I'm just going to pop that into my calculator, divide by 9.8, and then take the inverse sine to get the answer. And I get 42.78 degrees.